Second type of statements that we will consider are if and only if statements. So this means that P is true if and only if Q is true. So if and only if, or sometimes abbreviated as IFF. Such a statement means that P and Q are equivalent. So statements P and Q they are equivalent. So it means that if P is true, then Q is true, but also if Q is true, then P is true. Consider the following example. So let's say that we have, again, n as an integer. So consider n in the set of the integer numbers z. Then n is odd if and only if also n squared is odd. In this expression, in this example, the P statement is n is odd, and the Q statement, that one is n squared is odd. The way to prove such an equivalence is very simple. You prove it in two parts. You prove it as two implications. So you prove on the one hand P implies Q, and you also prove Q implies P. So that way you have shown both statements, P then Q and Q then P. To prove the implications, we can use any technique that we previously saw. So we can use any of the four techniques that we saw before. Let's start with the first implication, P implies Q. So you always indicate which part you are proving before you start to prove. P implies Q means that we assume P is true. So we assume that n is odd, and then we need to prove that n squared is also odd. We will use a direct proof. So we will assume P is true. So here n is odd. This means that I can write n as being 2k plus 1 with k some integer. So 2k plus 1 means that 2k is even. I add 1, so I make it odd. So n is odd. And then we have to look at what happens to n squared. So n squared, this is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is equal to 2 times 2k squared plus 2k plus 1. And so clearly n squared is also odd. So we now have proven half of the statement. We still need to prove the other half. The other half that we need to prove is that Q also implies P. So we have to prove that suppose that n squared is odd, then also n is odd. The way we will prove it is by contradiction. So what we will do is we assume that n squared is odd, but that n is even, and then we will find a contradiction. So here we have assume n squared is odd, but n is even. So if n is even, this means that we can write n as being 2k with k some integer. So then we can also look at n squared, but n squared just becomes 4k squared, which is 2 times 2k squared. And so clearly n squared has to be even, but we also assumed that n squared is odd. So we find a contradiction. The contradiction is often indicated with a lightning sign, and thus we proved that it is impossible. So here we have proved that it is impossible for n squared to be odd if n is even, because we found a contradiction. So this concludes the global proof, because we have now proved that P implies Q, and also that Q implies P, so there is clearly an equivalence between P and Q, so it's an if and only if statement, because both of the directions are true. One final remark for equivalence. Suppose we have an equivalence between P and Q, so P if and only if Q, then you can also negate this statement, and so you also get not P if and only if not Q. So sometimes it's easier to work with the negated statement to prove the negated statement instead of the statement itself, but they are the same. So if you can prove P imply or P equivalent with Q, then you also know not P is equivalent with not Q. For our statement, this would mean that if n is even, then also n squared is even, and vice versa. If n squared is even, then n is even. So there is also an equivalence between n even and n squared is even. The third type of statements we will consider are simple statements P. So we have a statement P, a single statement, but no implication. Actually, this corresponds to an implication, namely the implication true implies P. So if it is true, then P holds. Let's take an example. So this is the sixth example. Here we have a statement: the square root of 2 is an irrational number. So this is just a statement. It just says square root of 2 is irrational. There is no implication or no equivalence, just a statement and nothing else. Recall that an irrational number, so this is a number which is in R, but which is not in Q. So it's a real number which cannot be written as a fraction. The easiest way to prove such a statement is by contradiction. So basically you will prove that if P is not true, then you get a false statement. So basically what you do is you contradict this statement. If we then do this for our statement, we basically assume that the square root of 2 is a rational number. So we assume root of 2 is rational. So basically the root of 2 is in the set Q. And now we will go to show that there is a contradiction in this statement. If the root of 2 is rational, it means I can write it as a fraction, so I can write it as a divided by b, where a and b both are integer numbers, so both are in the z statement, and a and b have no common divisors. If then root of 2 is a over b, this also means that 2 is a squared divided by b squared, or a squared is 2 times b squared. So this means that a squared is even, and we've shown before that if a squared is even, then also a is even. If a is even, this means that a is equal to 2k for some k, an integer number. We thus have that a is 2 times k for k integer, and we also had that 2 times b squared is a squared. We replace a squared by 2k squared, so this is equal to 4k squared. This then means that b squared is 2 times k squared, and thus b squared is even. And if b squared is even, then also b itself is an even number. Hence, we have now that a is even, b is even, so both of them can be divided by 2, so they would have a common divisor of 2. But we assume that they do not have any common divisor, so this is a contradiction. It is impossible for them to have a common divisor of 2, because we said there are no common divisors between A and B, so we have found a contradiction which concludes our proof.